Thank you everyone for coming. It's a big group, even though we had the gala yesterday, so that's nice to see. So today we will be looking into Linux rootkits. I am a security research engineer at Elastic, at the threat research and detection engineering team. I basically do some malware analysis, dynamic analysis, basically just research into Linux malware. And today I'm joined by Remco.
Yeah, my name is Remco. I'm also a security research engineer. I work within the Elastic Security Labs team, and I primarily focus on Linux malware, reverse engineering, and maintaining our beautiful blog.
All right, so since we're focusing on Linux today, we will start with a little overview of how the Linux rootkits have evolved over time. And to better understand the differences between these different rootkits, we will explore the hooking techniques that they employ. And we wanted to publish research about the whole landscape, and therefore we collected an extensive list of Linux rootkits. And those are both open source and also closed source, actually rootkits used by attackers, to analyze and collect statistics about. And then finally, with the background knowledge that we have, we will be looking at Pumakit as a case study, and finishing it off with some detection engineering that may help you detect rootkits. So rootkits are basically just malicious software designed to hide processes, files, and activities, and themselves. And on Windows, they're typically like kernel drivers or bootkits. But for Linux, they also have little userland tricks like LD preload rootkits, loadable kernel modules, or nowadays newer interfaces such as eBPF and IOU-ring. So their goal is basically stealth and persistence and evading for as long as possible. But they're not really defined about what they try to hide and keep hidden. The mechanism itself doesn't really matter. Like it's mostly for detectability that it's useful to understand these. So we'll start with a little evolution of Linux rootkits. So we first have the userland rootkits with our shared object rootkits. And they manipulate the dynamic linker through dynamic linker configuration files or LD preload to make sure that they are loaded before any other program. So by doing that, they can hook userland, like libc functions, and use that to hide processes, files, network connectivity, and other events. So depending on the injection technique, a userland rootkit can either run for like a single user or system-wide. And they're still effective. They're in use today, but the limitations is that if you use any like statically compiled binary, you will easily spot these rootkits. So they're quite simple to detect. And because of that reason, attackers moved over to the kernel as well. And within kernel space, what we see are loadable kernel modules or drivers. And these reside in kernel space, and they basically have full privilege over the system. So they can hook syscalls, kernel structures, functions, basically whatever they want to do the action that they need, such as hiding themselves, hiding files, processes, networks, but also implement like backdoors, implement C2 communication, and also ways to instantly bump up to root privileges. The limitations for kernel space, loadable kernel modules, are that they can easily be blocked by enforcing kernel module signing. So if you don't have the signing key, then you will not be able to load your module. And they're generally kernel dependent. So often we see targeted attacks specifically by these loadable kernel modules because you can't just compile them and run them on any system. And another thing is that they're very crash prone. So for example, if you do like any distribution update, you might as well just crash the rootkit and thereby also the whole system, which is pretty noisy. Next, we have eBPF. This we have mostly seen actually by researchers. We don't really know of any in the wild use of eBPF-based rootkits. But these eBPF-based rootkits, they basically leverage the in-kernel eBPF virtual machine that allows like small verified programs to run in kernel context without actually the program being in the kernel itself. So attackers can attach eBPF programs to kprobes, tracepoints, Linux security modules to hook and intercept or manipulate any behavior that they want, achieving basically similar effects as the loadable kernel module. So eBPF was implemented in Linux 3.18, and it got mature around 4.9. So that is also one of their limitations. The system that you employ this on also needs to support these eBPF functions that you're using. It's also quite visible. So if you are running an eBPF rootkit and you're not really using eBPF tooling on your system, any eBPF hook in your system will be noisy. So that's also an easy way to detect it. And it runs in the kernel, but under very strict verifier rules. You can't just run any code in eBPF. There's a verifier with limited helpers. And because of that, it's also limited in what it can do compared to what an LKM can do. And finally, we have IOUing, which is the new duck in the bite. I guess that might be how you say it. But this is a technique that was only recently discovered by researchers. And it abuses the IOUing asynchronous I/O system to do operations such as read and write without requiring the traditional syscalls that we used to see with other rootkits. So they provide a certain element of stealth because many EDRs specifically hook the traditional syscalls to gather telemetry, but not the IOUing syscalls. So in that sense, it's quite stealthy. But it also has its limitations. It's only available from Linux 5.1+, and there is no real way to mimic the execution syscall. So you can mostly do read-write and network connectivity. And the liburing package, which is needed for this rootkit, is also not available by default. So setting it up is also rather noisy. Then I'll hand it over to Remco.
Yeah, thank you. Thank you for the introduction. As Ruben said, we took a look at a bunch of rootkits. We did some statistical analysis. And just to give you a view of the data set that we were working with, we collected 34 Linux families, not just samples, we had multiple samples per family, of course. And it was a combination of closed source, open source groups. Now, if we look at the amount of rootkits that we find, we see that the bigger part of the rootkits are kernel-based rootkits. So about 60% are kernel space, and that makes total sense actually, because if you want to be really stealthy, if you want to really hide what you're doing, you need to be in the kernel to control every aspect of the system. Now, still 35% of the rootkits that we found are userland rootkits. There's still a significant amount of samples there. And last but not least, about 6% are eBPF-based rootkits. As Ruben said, eBPF, especially in the rootkit world, is quite new, and we do expect that there might be a few more variants coming up in the upcoming years. But right now, it's only a very small portion and mostly research-based families that we see. While we were looking at the data set, we mostly focused on the hooking techniques that they employed. And here's a list of all the hooking techniques that we found in all the samples. Just going over top to bottom a little bit. First, we had IDT hooking, that's interrupt table hooking. Somewhere in the kernel 2x space, this actually became obsolete because the technique just wasn't used anymore, isn't viable. It was used by hijacking the entry point for the int80 interrupt call. That's no longer used in modern kernels. Syscall table hooking is basically you find the syscall table in memory, you replace the handler with a pointer to the function that your version of the function. However, that became obsolete in kernel 6.9. Notice the little star. We will get back to this. We have a little surprise midway through. But there was a change in kernel 6.9 that made all rootkits that use this technique completely obsolete. Inline hooking, basically find the function that you want to hook, change the first few bytes into a jump to your own function. It is possible, but there are measures against it to prevent changing of executable code, stuff like that. VFS hooking or virtual file system hooking, still viable, but you can only change the read and write operations for certain files, so you're very limited in what you can do. Now the last group, I'll take those three all together, after escape probes and eBPF. They're all debugging tools, tracing tools that are already present in the kernel, but they're made for tracing, made for observability, made for debugging, and they're being abused by rootkits to do their bidding. However, because they're not made for like complete control of the kernel, there are limitations. So rootkits, if they want to use it, need to like do some tricks, do some weird stuff, which makes them more visible again. I do invite everyone to read the extensive paper that we wrote. I think it's like 30 pages long, going into like every single detail and every single statistic for the rootkits. We don't have the time to go into everything today, but we'll go over a few high-level statistics. One of them is the top 10 syscalls that are actually being hooked by multiple families. We looked at this in order to find like similarities, and we differentiated between syscalls and normal functions. Now, if we take a look at the top 10 kernel rootkits, top 10 most hooked syscalls, we see getDank64 and kill in the top, which makes perfect sense. Those are the syscalls that you need for hiding yourself, and kill is often, but not always, used as a communication channel between user space and the kernel. Same goes for the top 10 functions. The top function is called some lookup name, and that also makes perfect sense, because that is a typical function that almost every rootkit uses to find other functions within the kernel. Other than that, we see functions being hooked to like hide TCP traffic, which is the idea of a rootkit hiding itself. In userland rootkits, again, nothing spectacular there. We see a lot of functions being hooked for reading files, opening files, so hiding themselves from the user. Now, with all these statistics, we didn't find any surprising facts. And you might ask yourself, like, okay, then why are you presenting that? Now, what we did find was that there is a simple and logical correlation between the amount of hooking that's going on within a rootkit and the maliciousness of it. Like, the more functionality that a rootkit has, the more hooking that is being done, and it makes perfect sense. We often see like publications, research publications with a rootkit as a proof of concept that has one function, two functions being hooked just to prove that it can be done. But in the wild, rootkits have 20, 30, 50 functions being hooked because there's a real attacker needs to like take over the entire system. Take over the entire system to be actually useful. Another thing we looked at is detection statistics, and this one was actually really surprising to me. What we did, we took the top 10 most used rootkits. We downloaded them from VirusTotal, so we didn't even compile them. We took like known samples, and in the first column you see the basic amount of detections that they had. Most of them, except for broke PKG, are between like 30 and 40 engines that flag these files. What we then did is we took that file and we stripped the debugging symbols. Nothing else, just strip debugging information. Uploaded it again, and you see that we dramatically reduced the detection size, just purely based on the files. But some of the engines were just completely gone. Like one detection was left for COVID. The last column was also really surprising to me. We took the same samples, didn't strip them this time, but just add a single null byte at the end of the file. That changes nothing for the functionality. The outloader will happily load that, but still we could dramatically get the amount of flags down. That means that at least the vendors that are detecting, they're not detecting based on adding just a single null byte, they're detecting purely on hashes, which is something that was done in the 1990s, but it shouldn't be the way to go in this day and age. One of the rootkits that isn't in here, and that's because we were found in the wild, is Pumakit. That's our case study that we looked into. We published a report on this last December. And here in the image, you see a high-level overview. again, because of time, we'll just fly over it a little bit. Pumakit was a rootkit that had its own loader. The loader was meant to disguise itself as a legitimate cron binary. It would load the legitimate cron binary, but at the same time load its own rootkit component. It would then be loaded into the kernel, install its own userland component, and after that, it started using its capabilities for Evo. What are those capabilities? A lot of stuff. This rootkit was very, very extensive. We saw it did connection concealment, disarming SA Linux, tracking what programs were being launched, hiding files in directories, and a very extensive function for credential theft. The images on the right, you could see what strings they were looking for. So they were looking for password prompts, private keys, anything. And those would be stored into a hidden file and then sent to a C2 server. The communication channel between userland and the rootkit was also interesting. In the beginning, I said the kill syscall was often used as communication for rootkits. They used to remove their command. And you see an example in the bottom. If you would type remove their Zarya, that's the keyword, and then .c.0 would mean return the configuration. So at that point in the return value, you could see the configuration of that rootkit. And they had like 15 commands that they used in that way. Now, we said we were looking at hooking techniques. Pumakit also employed multiple hooking techniques. They used ftrace, and this is the code example. They used ftrace to hook tens of functions within the kernel, mostly for file and network operations. They also used syscall table overrides. And this is a classic example. You basically see that they found a pointer to the syscall, and the version that I made red is syscall number 3 that's being replaced by the hooked sysread. Syscall 3 is sysread in Linux. But they also did something very interesting, and that gave me an idea. If you look at this code example, they were looking through the functions that they want to hook for a E8 byte. And if you disassemble a x86 binary, you will notice that E8, as seen in the lower picture, E8 is the start of a call instruction. They also were looking for this, the byte sequence. And if you look at that and the correct endiness, you'll see that that is the typical function prolog. However, and within the rootkit, this is the function prolog that skips a call to fentry. And fentry is the injected call to the tracing tools like kprobe, ftrace that the kernel injects. Why did they do this? They want to find the actual start of the function so they can hook that without messing with with the existing ftrace infrastructure. That gave me an idea. And bear with me, I've got like 2 more slides and then I've got a really cool surprise. First, let's look at some kernel code. Pumakit deployed syscall hooking, and I, in the beginning, said syscall hooking was dead. That's right. Pumakit wasn't compatible with kernels 6.9 and above. And this is why. If you look at the code in kernel 6.8, so before 6.9, this was the way that syscall table was built. There was an array being built with syscalls and pointers to the exact handler. In 6.9, they changed that. Now the syscall is a switch statement, and based on the number given to the switch statement, the correct function is called. Now, if you write a quick switch statement in C, compile it, and then decompile it, this is how it looks like. You see a list of calls, and I noted E8, the call instruction, and then it's followed by an offset based on the current instruction. Now, it turns out, if you look at a function with a switch statement, and you look for E8 bytes, followed by a specific instruction, followed by a specific offset, that is quite unique. Within an entire function, that only appears once if you're looking for a specific function. And that gave me an idea to think, hey, if I can do that, maybe I can replace that offset with a function that I wrote and basically hook the syscall table again. And that's exactly what I did. We called the technique FlipSwitch. We're flipping some bytes in a switch statement. We published it on GitHub, and while I was working on the stage, I realized I forgot to make the repository public. But this is the address, and in about 5 minutes after the talk, this is the address where you can actually find the code. The QR code is just the URL, and for the next slides, I also included the QR code. Now, in order to prove that it works, this is a system with a modern kernel, 6.14. We compile a debug version of the FlipSwitch rootkit. We then insert it into the kernel. Then show you that at this time I'm not root. I have a lot of groups, but not root. I'm using the kill 64 to elevate myself to root, and now I have root. And of course, I mentioned before, I do believe that Linux deserves way more research time than currently is given. Because if we upload our newly created rootkit, we have exactly one detection. And that's cheating because I made the rootkit, so I also made the signature, of course. But in all honesty, this should not be just one. It is a very simple rootkit. I didn't do a lot to obfuscate it, and it's still just not detected. Ruben? Sorry, 5.
All right, so usually when you practice in the hotel room, it actually goes slower than on stage. But this time, it actually went faster in the hotel room, so we only have like 5 minutes left. Yep. But here, we will focus a little bit on the behavioral detection. So when static detection fails, and it certainly will, as we just showed, it's interesting to detect the technique rather than the threat. So what we will show are detection queries written in Elastic, EQL, and KQL, but you can easily convert them to any language you want. And in the research paper, there are way more detection queries available, and also explanations. So if I go through them too quick, you can always just read the research paper, and yeah, you'll find all of them. So for shared object userland rootkit, one obvious one is you look at the creation of shared object files on disk, especially in locations where you do not expect them to be. Additionally, for persistence, shared object rootkits, they use the dynamic linker configuration files, which is located either in the LD preload files or the LD aso.configurations. So seeing creations, file creations there, or like appending to that file might be an indicator. And the modification of the LD preload environment variable. In this case, this query is looking at, or is expecting there to only be the LD preload environment variable, but you can simply add the specific LD preload environment variable to the query to detect that. For loadable kernel module rootkit, step 1 is actually loading the rootkit. This can be done through like a normal utility, like int.mod or modprobe. But most rootkits, or at least like most rootkits used by attackers, they actually use a loader. So if you detect process executions for these tools, you will not find them. But bottom line is, every rootkit that goes into the kernel needs to call the init module or finit module. So on the top, you can see an order D configuration. It basically says that it will look for the finit module and init module syscalls. And then if you actually try to load a kernel module, one of these events will pop up, which is one that you can detect. So during the loading phase, depending on the configuration of the rootkit, it might actually taint the kernel, because the kernel doesn't expect modules to be loaded outside of the kernel source tree. So if that happens, in your D message or your kernel logs, you will find a loading out of tree module tainting the kernel, which is an event that you can look for. And same for unsigned modules. So if a module lacks the valid cryptographic signature, then it will also say that in this case it's the revenge rootkit, module verification failed, signature and or required key missing, tainting the kernel, which you can flag on. This is actually showing the kill signals. So a lot of rootkits, for example, like diamorphine, they use the kill command to perform actions. And within Linux, the kill signals 32 to 64 are generally not being implemented by any known functionality. So that is the reason why rootkits typically use these signals. So if you write a query that looks at all of the signals above 32 up until 64, and you see these being used, that might be either custom logic for a program or suspicious. And then again, what I said, loadable kernel modules, they like to crash. So looking at seg faults coming from the kernel is interesting in general, because you would like to see when your kernel is actually creating seg faults, but it might also be a sign of a rootkit there. So for eBPF, there are two syscalls that are interesting, or one syscall that is interesting, which is a BPF syscall, but it has several elements that are interested to take a look at. So you have the BPF map create, lookup element, and update element, which are used to create, read, and update the maps, which are the kernel key value stores, and the BPF program load and attach, which is actually used to load the eBPF bytecode into the kernel and attach the hooks. So if you create an AutoD configuration as the one in the bottom and try to find these specific syscalls, then yeah, if you tune out all of the programs that actually use these in a benign manner, because these are also used by normal tools, then you will be able to create like baseline behavior and detect the anomalies. The same for the BPF probe write user helper. This is a helper that the eBPF project created, which allows an eBPF program that is running in kernel context to actually write to user space. So this is one of the functions that is a little bit notorious within the community, and they're debating on whether to restrict or remove it, because it is used for many benign purposes, but is also perfect for malicious purposes. So when this function is used, they made sure that it is being sent to the syslog, just because it is that potentially dangerous. So if you look at your syslog and you look for the kernel process, you will, if this is used, you will actually see this message popping up. Next, we have IOUring rootkits. They use three syscalls: the IOUring setup, enter, and register. And these are used to initialize a submission or completion ring, execute the actual request, and pin or register files or memory buffers. So using an AutoD configuration like this will allow you to detect that within your environment. IOUring is not typically used, so if you see this and you don't expect IOUring in your environment, you're down for a nice little investigation. Loadable kernel modules. If you load a loadable kernel module, it will not be there on reboot. So a loadable kernel module always needs to add some sort of persistence. So in this case, you can either add persistence in like an etc modules file, or in a mod probe configuration, or in the modules load directory. So looking for any file creations or appending to these files will show you like the actual persistence technique of the kernel module that is being loaded. UDEV rules. This is one actually used by Reptile. Reptile, I think, was the first one I saw it being used at, which is basically the device manager. So whenever a device is added with major number 1 and minor number 8, which is basically creating a new device that is using the dev random device, then the lib UDEV reptile loader is being executed. And because dev random is used for cryptographic operations, this will commonly execute during reboot, but also for OpenSSL kind of actions or certain programs. So that's an interesting trigger. General persistence techniques. You probably all know about these, but figuring out like systemd units and timers, cron jobs, initialization scripts like init, initd, or rclocal, and the pseudoverse configuration file are persistence techniques that we commonly see being used by rootkits. And they also use certain defense evasion techniques. So for example, this one, it was also shown or seen by Pumakit. So Pumakit is living in the kernel, but they also want to do user space activity. So what Pumakit did is they spawned a malicious, or well, not really malicious, but a fake kernel worker thread from the kernel that actually executes bash commands. So if you see a K worker or a K thread process parent that is not actually a kernel, not actually spawned by the real init system from Linux, then that's quite suspicious. And what rootkits commonly do once they're loaded is they try to hide themselves. So they know that loading a rootkit will commonly end up with logs being created. So what they do is they either try to delete or overwrite different log files, like the dmessage, but also kernel logs, syslog, boot logs, the messages in general. So that's a proper sign that you should be looking out for. And they also clear shell history quite commonly. So if you see your shell history being deleted, then that's also a pretty bad sign. I'm almost done, don't worry. And for the final few, we have some defense evasion techniques. So also the kernel message buffer clearing. You can do that through dmessage, but also journalctl. There was just a new rootkit being published called Singularity that used journalctl to do this. So you can detect those. And finally, we have time stomping. So once a module is loaded, it will alter the timestamps to make it look like it wasn't just uploaded today, but actually corresponds with the different files on the system. So they can use touch for that, but there's also other ways to do time stomping. And then finally, minimizing attack surface. Let's go through that quickly. So keep your kernel up to date, always nice. Doesn't really secure you, but it's always a good thing to do. Kernel hardening, implement secure boot and signature enforcement. This will especially help for loadable kernel modules. You can install kernel protection tools like the Linux kernel runtime guard, which will at least show you when certain actions by rootkit are taken. You can do behavioral monitoring with like AutoD, file integrity monitoring, implement like an EDR. There's access control frameworks that you can use like SELinux and AppArmor. Of course, if you're root, then you can also disable these, but you can still restrict root users via these utilities as well. So that is interesting. And then you can do periodical active scanning, but maybe the most important one is just try to minimize your initial access factors, because if you do not have SSH with a bad password to the internet, then I think already 80% of the issues are gone. So yeah, thank you. That was our presentations. And if we even have time for questions, then feel free.
Thank you.